2021. Maya is taking AP Physics. Carp just assigned a cockamamie circuit for her to solve.
I must choose a sidekick.
The choices are J. John, fitness Instagram influencer turned physics tutor. Mad Maggie B, educational rapper, hardest in the game, has a face tattoo. Ben Eni, TV chef, best known for his series Cooking with Kirchhoff. Or JMillz, an educational mastermind and founder of Joe Academy, whose videos have trillions of views.
JMillz is the obvious choice.
JMillz here. Now we're going to learn circuits for dummies. Alright, boys and girls, today we're going to try to simplify Carp's cockamamie circuit. I already redrew it for y'all, so here you go. No, I intentionally didn't put in the currents in this picture because that's not what we're going to focus on right now. We're just going to focus on trying to simplify the resistors. So we're going to start with resistors in series. Resistors in series look like this. They're just along the wire. Basically, they're along the same wire and they function as one resistor. So R1, R2, and R3 add up to Req. And the equation for that is Req equals R1 plus R2 plus R3. Pretty intuitive. So there are a few resistors in series in this first circuit, the most unsimplified circuit that we can solve right off the bat. So that's R1 and R2. We're going to call that Req RA. R4 and R5, call that Req RB. R9, R10, R11, call that Req RC. And R7 and R8, call that Req RD. So I'll talk you through the equation for RA. So we're just going to add up R1 plus R2. 20 plus 5 to get 25 ohms. That's what RA is. You can do RB, RC, and RD on your own. I believe in you. You're smart enough. All right, now that we've done our first simplification, let's do our second. Right now, we're going to look at resistors in parallel. Let's go, boys. So the way I like to think about resistors in parallel is current comes in one way, has multiple paths to choose, can choose any of these, and goes out the other way. It must enter from the same point, have a junction, multiple paths to choose from, and exit from the same point. And all of these resistors, Rx, Ry, and Rz, function as Req. How do we find the value of Req? Simple equation. 1 over Req equals 1 over Rx plus 1 over Ry plus 1 over Rz. So, do we have any resistors in parallel here? Yes, we do. Ra, R3, and Rb. So we can simplify that. Oh, what else? Rc and R12. Oh, nope, trick question. Note this path here. The current is always going to take the path of least resistance, and since there's a path with 0 resistance, we can just nix out RC and R12. All right, so now let's deal with RA, R3, and RB. I did the equation for you. We're going to call that Req Re, so 1 over Re equals 1 over Ra plus 1 over R3 plus 1 over Rb. Plug and chug, and we get Re equals 3.659. Okay, here we have our most simplified circuit that we've been working towards. Remember how I said forget about current before? Current's back, and current in this problem is a bish. So we're going to use Kirchhoff's law to solve current. If you're not familiar with them, we'll do a quick overview. But for basically the way you start is you guess which way current is going. So I took a liberty of guessing that current is going clockwise. I drew in the currents starting with I1. Whenever I got to a junction, got to split the current, new current value, I2, I3. So I1's going this way, splits into I2 and I3. I kept going. I3, I4, I5, I5 goes here, splits to I6. Boom. All right, basically Kirchhoff's junction rule, the way it works is the current flowing into a junction must equal the current flowing out. So in this case, IA equals IB plus IC. Or if we were going to reverse it, drop it in reverse, and the current was flowing this way. Boom, boom, IB plus IC equals IA. Oh wait, those equations are algebraically equivalent. Crazy, that's why it doesn't matter which way you draw your currents if you chose clockwise or counterclockwise. Alright, anyway, so now that we know that, let's start building our system of equations. So here are the junctions in this problem. I'll help you build the first one, then you can build the other ones for the other junctions. So I1, we're going along, splits into I2 plus I3. So I1 equals I2 plus I3. Boom. Now, for the other junctions, these will be the equations. I believe you can get those on your own. Now, we can do some simple algebra to figure out that these are our junction rule equations, and that's what we'll be using when we build our total system of equations. So now let's move on to Kirchhoff's second law, the loop law. All right, now that we're done with Kirchhoff's junction rule, we're going to use Kirchhoff's loop rule to finish building our system of equations. So Kirchhoff's loop rule states that the sum of all the potential energies around any given loop is zero when we look at a circuit. This makes sense when we think about conservation of energy. Any energy added into the loop by a voltage source must be lost along the way. Think about resistors and such. So when we're building an equation using the loop rule, first we're going to choose a starting point, then we're going to move around the loop. I'm going to move clockwise, and then we're going to build the equation based off the elements of the loop. So for voltage sources, if you're moving from the positive terminal to the negative terminal, you should subtract the E value. If you're moving from the negative terminal to the positive terminal, you add that E value. So for example, here we're moving from the positive terminal to the negative terminal. We're going to subtract the E value. Now we're moving from the negative terminal to the positive terminal, add the E value. For resistors, if current is moving in the same direction as the loop is drawn, you subtract IR. If the current is moving in the opposite direction as the loop is drawn, you add IR. So let's say that current is moving in this direction, and we're drawing the loop this way. The current is moving in the same direction as the loop is drawn, we subtract IR. Let's say the loop is moving this way, then we will add IR. Okay, so let's build our first equation using the first loop right over here. We're going to start in this corner and move clockwise. So boom, now we've hit a resistor. Current is moving in the same direction as the loop is drawn, so we're going to subtract IR. So we're going to subtract I1 RE. Keep moving, hit our first voltage source, E1. We're moving from the positive terminal to the negative terminal, so we will subtract the value of E1. Keep moving, hit E3. We're moving once again from the positive terminal to the negative terminal, subtract the value of E3, keep moving. We've hit R6, current is moving in the same direction that the loop is being drawn in, So we will subtract I2 times R6, keep moving to complete the loop. We hit our third and final voltage source. We're moving from the positive terminal to the negative terminal yet again, so we're going to subtract T2. That's how we will build the equation for the first loop. Now, there's 6 loops in this circuit. You go ahead, pause the video, try to build the equations for the rest of them, and boom, here are the answers, color-coded in accordance to the loop. I believe in you. I hope you got those equations. I know you can. All right, hard part's over. Now that we have our system of equations, plug that ish into your calculator to get your answers. Here we go. So notice how some of them are negative. What that means is that you drew the current the wrong way. So since we drew all of our currents clockwise, that means I1, I2, and I4, which are negative, are actually counterclockwise. Figured out with their values. Oh, fuck. Flamvid, go away. Okay, whatever. Okay. So now we're going to go back to our original circuit, and I took the liberty of drawing in the values of the currents we just found and the directions based on the signs of their currents, which we just talked about. Anyway, so what we still need to do is find out what the value of I7, I8, and I9 is. So we will have to build another system of equations. So fun. So we know that I1 equals the sum of I7 plus I8 plus I9 based on Kirchhoff's junction rule, which we just reviewed. We also know that the voltage drop across the 3 different paths must be the same. And V equals IR. Remember that? So we know that I7 times the resistors along that path, I8 times the resistors along the path, and I9 times the resistors on the path must be equivalent. So that's how I built this system of equations. Plug that into your calculator to solve. There we go. Those are the values we get. And bada bing, bada boom. This is our final circuit with all of the necessary values in there. There we go. Now that we have solved for all the values we need in order to determine the voltage drop across the resistors and the power at each resistors, Let's do it. So to solve for voltage drop, you just use V equals IR. To solve for power, you just use P equals VI or I squared R, their equivalent. So I just did out some sample equations for R2, R8, and R14 just to show you exactly what's going on. But I made a table for the rest of the values. So here you go. This table lists each resistor and the voltage drop for it and the power so that you can check your own work. Now, the next logical question to be asking yourself that every single physics student out there should be asking yourself is, wait, so if I left this circuit running for 2 minutes, how much energy would be transferred from electric potential to thermal energy? And the way you determine this is you determine the total power in the circuit, which I took the liberty of adding all these up for you. It's 1.909 watts. And you multiply that power by time. The reason that works is because the units of watts are joules per second, and we're looking for joules, so we just multiply by time. So we multiply this total power times 120 seconds to get the energy released to be 229.11 joules. Excuse me, the energy transferred to thermal energy.
Let me check that in a PhET simulator. Of course JMillz is right. My hero.